Good morning, everyone. I appreciate being able to kick off this session. I'll be the other subterranean voids today. I think just to kick things off, why do void spaces matter? And in particular, it's really important for things like the in situ research utilization in astrobiology and understanding how much subsurface porosity or void spaces we have is going to be a critically required measurement. And when we talk about porosity, most folks in this community are thinking about the pore spaces available between grains. What I'm going to talk to you today, though, is about fracture porosity, which is porosity that's occurring because of faults and fractures. And this is a critical measurement that we have here on Earth because fracture porosity is responsible for the majority of our subsurface reservoirs, whether that be groundwater or oil and gas. And it's also really important for mineralization and trapping of gas and fluids. And so it's quite likely that fracture porosity plays a very similar role of trapping volatiles on other planetary bodies. And so being able to understand and quantify the locations and the magnitudes of fracture porosity is going to be a kind of critical next step to determining where subsurface volatile storage capabilities may exist. And so just to give you a brief view, this is a what we call a dilational fault going through stratigraphy on Earth. And the cave you see there is right down the road from me. This is a prime permeability pathway for groundwater. So the cool thing is that extensional fractures appear to be everywhere we look in the solar system. Now, as terrestrial geologists, we benefit from being able to go out and do field mapping and geophysics to try to understand and characterize this. But in planetary science, we often just have a gray fuzzy image. And so it's really difficult to infer what's actually going on in the subsurface. However, everywhere we've looked at these gray fuzzy images, including small asteroids, we see extensional fractures. Just because we see the extensional fractures, though, doesn't mean we can really quantify what the degree of fracture porosity actually is. And so that's where pit crater chains come into play. So pit crater chains are collapse features that are typically found along structural trends of extensional fault systems. So you see these in long chains. Now, they're hypothesized to form along either open mode fractures that are just opening up, or along dilational faults, which are similar, but they're dilating open. And so as these faults move, these faults and fractures can widen or dilate, and then the overlying material collapses into them. But because we know that that's likely the formation, these pits themselves actually give us a lot of information about what's going on in the subsurface. So we can use things like image data by just looking at sun angles to quantify what the size and volume of that pit is. Knowing that, we can get some lower bounds on what the void space under that must be to accommodate that material. As we add up all the pits in a chain, then we can start to quantify, or at least put lower bounds on what the porosity is in the subsurface. Now, we've done this on Earth to try to see just how well you can do this. So this is an example from Iceland, and on the surface, that's me quantifying the volume of a pit at the surface. That's my colleague, David Farrell, and the oval down there within the dilating segment of that fault. And so, just from these visuals, you can see that these dilating fault segments are actually quite large. I mean, I don't think I'd want to live there. We'll see some lava tubes that look much more hospitable for humans. But if I was a microbe, this is a perfect place. Not only that, but these are areas that, fluids are pretty lazy. They prefer to flow through a void space rather than solid rock. So these dilational faults and fractures become permeability pathways. And in this case, this is where the groundwater is flowing. Now, even if we don't necessarily have a pit crater chain, we can often see the open mode fracture at the surface. So just doing some basic calculations of the displacement, specifically being able to understand how much horizontal movement or heave, we can make calculations of that, an estimate of the depth of the dilation segment, and still get a pretty basic idea of how much porosity there is. Now, the cool thing is much like extensional faults, pit crater chains are everywhere. They have been identified on terrestrial planets like Venus and Earth. They've been found on icy moons like Enceladus. They've been found on small asteroids like Eros and Vesta. And so this gives us a really good opportunity to understand these various different worlds. I mean, these are widely different geologic settings, and yet we're getting the same geologic features. So it speaks to they probably have a common underlying formation mechanism, but it also gives us a common underlying methodology in order to understand them. And so just to conclude, life, including humans or otherwise, we often utilize resources that are found in the subsurface, most often along faults and fractures, that create permeability pathways for fluids and volatiles, as well as storage sites and mineralization in these same locations. However, being able to identify these subsurface void spaces is not easy with the remote sensing capabilities that we currently have. But I would argue that the ubiquitous nature of pit crater chains, from terrestrial planets to icy moons to small asteroids, make them a common surface marker that identifies potential areas of subsurface void space across the solar system. Thank you.